Welcome to class meeting 28 of Introduction to Optimization. Today we have the following announcements. First, homework number 6 is assigned and due on next Monday, so you have 1 week to work on. And you have additional 6 problems. Most of them are proof or derivation problems. First one is related to the proof of the necessary if and only if part for the convexity and Kkt conditions. Second one is to show that the water filling solution we derived really satisfies all the Kkt conditions. Third one is that, as I'm going to summarize in a few minutes, that deriving the dual LP problems for symmetric dual form and asymmetric dual form, which means that here asymmetric dual form has the standard form LP, but symmetric form primal LP does not have that. I'm going to show that. Fourth one is that in LP, in linear programming, the weak duality always holds. Of course, you can just use the you may use the you might use what we learned from the Stephen Boy's textbook, kind of more general weak duality, but I'm not going to ask that. You find the proof from the textbook, and you will be able to find the proof for the, I remember, for the symmetric form. You also need to do for a symmetric form. Got it? And also, you prove the strong duality, both for symmetric and asymmetric dual form. So what I'm saying is that do not use the result for the general weak duality, and do not use Slater's constraint qualification here. Got it? Okay. And for the sixth one, we are going to show the complementary slackness in linear programming for symmetric form. You also do that for asymmetric form. That's very easy, actually. So these are the homework 6 problems. So let's quickly review what we were at last time. So the topic of last lecture was the perturbation and sensitivity analysis for general constraint optimization problems with equality and inequality constraints. How many kind of lump to the topics did we have? We had 2 actually. The first was about the global sensitivity, and second one was the local sensitivity. Whenever you see local, most of the times it is related to what? Differentiability, especially continuously differentiable case. So here we assume that this P star UV, I'm going to define again, is C1. C1 means that it is once differentiable and the derivative is continuous. Okay. Anyway, the continuity is the necessary condition for the differentiability. So anyway, P is continuous, but P prime is also continuous. So given that, we define the so-called unperturbed problem and perturbed problem. So unperturbed primal problem looked like what? Just the standard constraint optimization problem with equality and inequality constraint functions. So we have f0x as the objective function, subject to the inequality constraint functions satisfies this inequality, and equality constraint functions have this condition. So given that there are many possible ways to perturb the problem, you may perturb the objective function, you may perturb the inequality constraint function. You may perturb the equality constraint function. There are many combinations you can perturb the problem. And unfortunately, for such general perturbation, you cannot reach some interesting results. So we considered a very special case where we perturb the equality and inequality constraint functions in a very special way. Got it? So we do not perturb this. We do not perturb these two in general way. We perturb these two in a very special way. What were they? We introduced perturbed primer. We introduced two vectors u and v. So instead of 0, we used u. Instead of 0 in the inequality constraint functions, we used v. Got it? So this is a very special way. Remember that. Okay? It's not kind of omnipotent. It can be used everywhere. It's not like that. Okay? It's a very special case, but very useful. Very useful in many cases. And unfortunately, in general, unperturbed primal problem, such a perturbation does not mean much. Okay? But in some special cases, for example, suppose the component functions of this inequality constraint function are all convex. What does that mean? Each convex function less than or equal to 0. Such a subset of X is called a sublevel set. Especially a sublevel set of a convex function has very interesting property. The set is convex, first. Second one is that if you increase the level, then the set expands. If you decrease the level, then the set reduces. Got it? So it has very interesting property. In that case, in such case, you may say something. For example, you increase u sub I. What does that mean when f1 is convex function? You increase the constraint set, right? In that case, what will happen in this minimization problem? It may be possible that you achieve lower minimum value. Got it? But I'm not saying that this is general. So in the global sensitivity analysis, you should be careful. You should be careful. Sometimes increasing u1 may reduce the constraint set depending on the component function. Or it may say nothing. For example, you do not reduce, you just move the constraint set by some offset. In that case, no inclusion or being included, that kind of argument can be made. Okay? But anyway, we derived the unperturbed dual and perturbed dual and utilize the dual problem to have some global sensitivity result. So the key was not just the perturbation and sensitivity analysis. We utilized the dual problems for unperturbed problem and perturbed problems to perform this analysis. Got it? So sometimes formulate some corresponding, almost equivalent new optimization problem. You may have some information. That's the big idea behind this analysis. And I found that I made a little mistake last time, so let me do this. So for the unperturbed primal and dual, let's define the Lagrange function or Lagrangian as L. And for the dual, let's say that the Lagrangian is L tilde. Now let's write down which one is what. So we know that the first component is the same. Second term is a little bit different. We introduce lambda transpose. And here goes fx. But here we have lambda transpose and fx minus u. And here we have nu transpose times x. Here nu transpose hx minus v. So far, so good. An interesting property is that this is nothing but L of x lambda nu minus lambda transpose u minus nu transpose v. So you see, the perturbation we use gives us very interesting, simple form of the Lagrangian. Now, what can we say? In the primal case, we have what? The primal optimal value of the objective function is lower bounded by L x lambda nu for all x in the, let me use this omega p, which means that the constraint set of the primal problem. Got it? And here, why this is not equal? Why this is not equal? By the way, I have to assume that for all lambda greater than or equal to 0. Why we don't have equality even though I assume x is feasible? Because as you see here, this is 0, but here each component is non-positive, and you have non-negative, so this could be some negative value. Got it? It is less than or equal to 0, so this is true. And what can we say here in the perturbed problem? Let's say that the optimal objective function value of the perturbed primal problem as p star uv, because the optimal value depends on our amount of perturbation vectors u and v. Now, we can say the same thing. Got it? Due to the same reason. Where the difference is that for all x in omega tilde of p, and for all lambda greater than or equal to 0. Now, what do we do? Usually what we do is that we infimize the Lagrangian, right? We infimize Lagrangian over x. So we have, the next step is p star is lambda nu for all lambda greater than or equal to 0. Here, this is the infimum of L over x in D, for example, right? You don't need to, you don't have to choose D. You just need to choose some subset greater than omega p. That includes omega p. Then you can have the same inequality, and that is a function of lambda and nu. So you can say this, right? So far, no problem. Now, this holds for all lambda non-negative and any nu. So we may maximize this G, and that is what? That is the problem of dual. That is dual maximization problem. And we have what? And this is defined as D star. Now, so far, we didn't assume any strong duality. Weak duality is what? Weak duality, I want to say that it's by definition. Okay? By definition, we have duality, but in our textbook, the dual problem is arbitrarily defined by the authors, and so they had to prove the weak duality. Okay, so that's the difference, but we are talking about almost the same thing. Now, what about here? if you just copy, probably what you want to do is to optimize this entire function, right, over x. Now, is it okay? See that here you infimize the Lagrangian over x. Here you infimize Lagrangian over x. But x is different, right? So what do we do? One good thing of choosing D is what? Here you can choose same D, right? So let's try this. Got it? So nothing's changing. The domain in the unperturbed problem, in unperturbed primal problem, is the same as the domain of the perturbed primal problem, right? Because we perturbed the special way. Okay, we perturb the problem in a very special way. Now, we do not want to proceed this way. We want to utilize this one. So here, by the way, what's interesting is that if you list up this L tilde, you plug in here. Since the infimization is over x, actually, what do you have? G tilde is nothing but G of lambda nu minus lambda transpose U minus nu transpose V. Am I right? Yeah. So nothing special. So far so good. But here we do not maximize this one over lambda and nu. We just plug in, see? Here, suppose the optimal solution to this unperturbed dual as lambda star nu star. You plug in here. Got it? Since this holds for all lambda non-negative and nu, this inequality still holds if you plug in these two here. So nu star minus lambda star transpose U minus nu star transpose V. Am I right? So here goes the difference. We do not maximize our perturbed dual function. Okay, they are different. So up to here, the procedures are all the same, but here it's different. We just plug this solution here. Now, what can we say is something? We have, here goes the assumption. What? For the unperturbed problem, for the unperturbed strong duality holds. If you assume that, what is this first term? What is this first term? Strong duality holds means that P star equals D star. What is D star, by the way? D star is G lambda star nu star. Got it? Got it? So this one is nothing but P star under strong duality. Okay, got it? So our global sensitivity analysis also has limitation. Our local sensitivity result required what? continuously differentiability. Now here our global result also requires some assumption. Otherwise we cannot say much. Got it? So and also this one could be said 0, 0. Because here if you choose u equals 0, v equals 0, perturbed and unperturbed becomes the same thing. So here you can replace this one with p star 0, 0. That's why you had this result last time. Probably I was not that careful last time, so I'm not sure, but I may miss the stars or some in the derivation I just hand waved, but this is exact now. Okay. Then what happens? Then what you can say always is that if this term is positive or that term is positive, so altogether if this term is positive, what you can say? Lower bound goes up. So in your minimization, what happens? Your performance worsens. That's what you can say in general. But under the convexity assumption like that, you can say more. Got it? Because in some cases, you know which direction this P star UV moves, goes down or goes up. So in that case, sometimes you can say that, okay, it goes down, but it does not go down much, something like that. Got it? But in general, you can say that when this is very large, your performance definitely worsens because your lower bound pushes up your minimum value. Got it? So I may spend too much, but anyway, this is global sensitivity result. So this is global. And it requires what? Strong duality of unperturbed problem. Duality of unperturbed ones required. Okay, second, local sensitivity analysis. You need what? You need P star UV is continuously differentiable. The result was very simple and meaningful. So you partially differentiate the optimal function value of the perturbed problem by u sub I. And also you can do the same thing for v sub I. Let me say v sub j. And what was the result? Okay, be careful. Local means what? Related to derivative, right? Derivative at what? So here, what you can say is very simple. You can only say near the unperturbed problem. Got it? This is very important. Near the unperturbed problem. You don't know what will happen to some perturbed problem and you perturb more. You can't say anything. What you can say is that if you perturb the original unperturbed problem little bit, then is it true? No, you need star because we defined lambda star, nu star are dual optimal for the unperturbed problem. Got it? So it's kind of interesting. See that? What happens if you increase ui? Then P star, if this is negative, decreases. If this is positive, increases, right? Because this is related to the slope of variation. If slope is positive, if you increase this one, then this one increases. Got it? Same applies to this. Okay? We don't need what? We don't need strong duality. Did we? Okay, I remember we needed that. Just a second. Let me check. Okay. Yeah, somehow I remember I needed that. Just a second. Where it is? What was the proof? Yeah, I think we need strong duality. Otherwise, it does not make sense. Okay, because we still use this in the differentiation. So let me retract. Okay, so weak duality also requires strong duality. The local perturbation sensitivity analysis also requires this one. Okay, so strong duality of unperturbed problem required for both this one. Okay, yeah, it's confusing. I'm sorry about the confusion. Okay, anyway, under the strong duality of unperturbed unperturbed problems. Okay. Anyway, that was all about the sensitivity and perturbation analysis. And our next topic was the LP problems. We've seen that any LP problem can be put in the standard form. What was the standard form, by the way? Standard form linear programming problem. It's a minimization problem subject to what? X is in the first orthant, and what? You have equality constraint function that is affine. But here we need something more like this. First, B must be chosen as a non-negative vector, and also we assume that B is in the range of the column space, in the column space of A. Otherwise, we have an empty constraint set. Okay, and we also assume that here A is fat matrix, and we may remove some variables so that we may claim that rank of A is just simply M, and here M is less than or equal to N. Okay, that was the standard form linear programming problem. And as I stated here, what you need to derive is this one. So here, if you derive the dual problem, you will see some maximization over lambda. You may not like lambda. If you follow the convention we used for lambda and nu, this must be a function of nu. That's what I remember. So nu transpose B subject to, what was that? A transpose nu less than or equal to C. Okay? Yeah. By the way, you may say that, well, I have to introduce lambda for this inequality constraint function and nu for equality. But where is my lambda? And actually, we derived this and actually showed that lambda is just a slack variable or something. Okay, I do not remember, subplus or slack variable. So we could remove lambda in the dual problem. Got it? And unfortunately, as you see that, the mean changes to max. But here, equality constraint is changed to this. But equality constraint is changed to this. But where is the inequality constraint? Changes to, for example, equality constraint. So people say that, okay, there is no symmetry here. That's why this is called asymmetric form dual. So this is a symmetric dual form. Got it? So Standard form LP is related to a symmetric dual in LP. Now, then what is the symmetric form? Here is max. Okay. Here goes the symmetric dual form. And that looks like this. As we've seen in the dieters problem and drugstore owners problem, the problem is given like this. You minimize C transpose X subject to AX greater than or equal to B. So in dieters problem, you want to at least satisfy the minimum daily requirement, right? So that's why you had this form. And also, you cannot take the negative value of some food, so you had this. Now, in a very special case where every CI, yeah, these are all non-negative, and in two-dimensional case, this looks like your high school LP problem like this. So this is our omega, the constraint set, and you want to find the minimum objective function value that a straight line with negative slope can achieve. You've seen a lot of such problems. Now, what is the, so this is primer. What is the dual? As I told you, you need to show in your third additional problem. But the result is very simple and looks like this. You maximize a lambda transpose B. This is same as in your asymmetric form. Okay, but here it was nu transpose B. But here you have lambda transpose B. Am I correct? Let me see. I believe so. And here, subject to A transpose lambda less than or equal to C, and lambda greater than or equal to 0. Okay. So, as you see from here, this is definitely related to the Lagrangian dual variable corresponding to X. Because we want lambda greater than or equal to 0 in finding the lower bound. Okay. Anyway, so show this. Got it? Now, let's assume the same condition. So all parameters are real positive. Then what happens? Here is the lambda 1 axis, and here is lambda 2 axis. And what do you have? Your lambda resides in the first quadrant. And what is this? If you plug in 0, then this holds, which means that this becomes the constraint set of the dual LP problem, and you want to find out the straight line that touches probably here in this case. So remember this. It may help you a lot in remembering the symmetric form primer problem and symmetric form dual problem. Okay? If you remember this, it's piece of cake. Okay? See that if you plug in 0, this does not hold. That's why you have this area as your constraint set. Here, if you plug in 0, this inequality holds. That's why you have this area as your constraint set of the dual problem. Got it? So derive this. It's not that difficult. Just use what I told you, how to define the Lagrangian, and you optimize, you infimize the Lagrangian function to find the dual function. And sometimes you remove the variable lambda. Here, you need to introduce two lambda variables for two inequality functions. But anyway, you will end up this. Got it? Okay. And what's the next? For weak duality. Okay. So now, let me see. Yeah. Here, let's do the same thing for the. So this is a symmetric form. Just a second. So here, let's try to draw the constraint sets for the asymmetric primal and dual. Okay, you see the difference here in two-dimensional case. This could be what? This could be a line segment, for example, right? When all the variables are positive. So this line segment is the constraint set. Okay? And you want to minimize the value. Got it? Here in the dual problem, so let's plug 0 here. What happens? This is included. But you don't have equality constraints. So interestingly, you have something like this as your omega d. This is omega p. Got it? So in both symmetric and asymmetric form, you see something similar like this. A transpose nu less than C. A transpose lambda less than or equal to C. By the way, our textbook just used lambda. It doesn't matter, right? It doesn't matter. You can choose any variable. Got it? Okay, here goes the some properties. So let's go to our lecture note 17 dash what? Yeah, page 4. So properties of dual problems. Is it page 4? Yeah. So here the authors say that we discuss some fundamental properties of duality problems in both symmetric and asymmetric forms. Sometimes the results are a little bit different. That's why I asked you to work both for symmetric and asymmetric form. First, weak duality lemma. And it's very easy to show this for the, what was that? One of the symmetric or asymmetric form. The other is a little bit different, but anyway, this is your first problem, right? So work on it. You can do it. It's not that difficult. So first, weak duality. 2, strong duality. To prove the weak duality, you should be careful. What you are proving is this. If X is feasible and lambda is also feasible, then C transpose X, if I remember, is greater than or equal to lambda transpose B. Of course, depending on your choice of symmetric or asymmetric form, you can change this to nu, but it doesn't matter. Okay, got it? I'm not saying that these are optimal solutions. I'm saying that as far as these are just feasible, then this holds. Got it? Now, the strong duality says this. You have the same condition and X is primal optimal and lambda is dual optimal. As I told you, again, lambda could be new in your asymmetric form. Then what? What you want to show is this one. Got it? So you have this additional assumption. As you remember, usually weak duality holds for what? Primal optimal and dual feasible, right? Am I right? Primal optimal and dual feasible. You remember this, right? In our minimization problem, we find the lower bound. Right? So precisely speaking, actually, if you choose some corresponding primal dual, then this holds. But if you choose, for example, this one and that one, inequality does not hold. Am I right? So you should be careful. But actually, the situation is not that. Anyway, I may not, I'd better not say this. Anyway, so this is what you are going to prove. Got it? So it's not that difficult. Just follow the proof in the textbook and derive your own solution for the other case. Textbooks sometimes proves the weak duality for example, symmetric form only. You do it for asymmetric form. Strong duality for symmetric form. You do it for the asymmetric form. Got it? Not that difficult. But do not use the result of convexity and Kkt and Slater's such thing. Don't use that. Okay. Now, here goes duality theorem. So here, primal optimal problem has optimal solution. This is the assumption. Then what? The dual has also optimal solution. And what? Optimal value of their respective Auxiliary functions are equal. What does that mean? Strong duality holds. So this can be understood as what? An existence theorem. If optimal solution exists for dual, optimal solution for the optimal exists for the primal, optimal solution exists for dual. Got it? So this is an existence theorem. As I told you, existence theorem is usually hard to prove, but very, very useful. Sometimes it's straightforward to prove, but in general, you feel that it's a hard problem. Anyway, the proof consists of two claims. So first, from here, where is claim? Yeah, from here to here, you have the first claim and proof, and then you have the second claim and proof, and that gives you the proof of this. Okay. Here, the important thing is this: you are just given an optimal solution. You have to show that lambda exists. One way is that you find that. Okay? Many existence theorems are not in this form. You cannot find what you want to show to exist. But here, this existence theorem is very easy because it's very easy to spot that corresponding lambda. Okay? And actually, that is this one. And you remember, what is this one? Actually, the ideal proof in this theorem is you utilize the simplex algorithm. That's why this appears again. So as you see that if the solution exists, then from the fundamental theorem of linear programming, optimal basic feasible solution exists. So you somehow say that, okay, if X is optimal, then we can find the canonical tableau. Okay? And let's utilize that. That's the idea of this proof. And I'm not going to cover everything. What I want to emphasize is this one. So here we utilize the simplex algorithm. So I told you once that the simplex algorithm is not the only algorithm that solves linear programming problem. It's one of many linear programming solvers. But here, improving some results, we can utilize that. And simplex algorithm is simple enough to understand. That's why we studied that. So read this carefully. But the idea is this. This is an easy existence theorem. You just spot that lambda and show what? C transpose X star equals lambda transpose B star. So it's very easy existence theorem. So I'm not going to cover that. Is it assigned as the homework? Seems not. Yeah, it seems not. But anyway, no, I did that, right? No. Okay, so that is not assigned, but you can do it. So the existence theorem says that. So duality theorem. If X star is primal optimal, then there exists lambda star feasible and what? That is dual optimal and P star equals D star. Okay. And proof is simple. You just find lambda star. Okay, next one. By the way, the consequence of this theorem is summarized here. Consequence of the theorem is summarized here, and you need to study this. Okay, it's a little bit confusing. Not that important, but a little bit confusing. The result is simple, but try to reason why this is the consequence of the duality theorem. Okay, it's all up to you. As you experience, feel today and tomorrow in our, as I announced that this Wednesday's class meeting is moved to tomorrow. Okay, let me write it down here to 8. Okay, so here Wednesday class, Tuesday 8 p.m. And I'll cover very fast because most of the topics we already studied in our general study on duality. Okay, the next one is the duality and simplex method. And you don't need to suffer a lot. Okay, actually this is piece of cake. Okay, as I told you, just the duality theorem itself requires simplex algorithm. Okay, actually part of. So anyway, you can easily find that simplex algorithm is very useful in proving the results in linear programming. Example can be understood very quickly. It's a piece of cake. Now let's see the complementary slackness. You remember what was the complementary slackness for the general primal and dual problems? What was that? We introduced lambda non-negative and what? Lambda non-negative time transpose the inequality constraint function. So we had something like this. Where lambda star greater than or equal to 0 and fx star is less than or equal to 0. Okay? This is what? this is from the assumption, dual feasibility. And this is from, primal feasibility. And this is from dual feasibility. And what does this mean? Each term in this sum becomes 0, right? That was complementary slackness originally. But it seems that this is a little bit different. Consider a standard form LP. Standard form LP. What is this then? This is simply lambda transpose X is 0, right? Nothing more than that for the standard form LP. Am I right? Because this Lagrange multiplier vector is for the inequality constraint X greater than or equal to 0. So this F is simply X. So the complementary slackness means lambda star transpose X star equals 0. Am I right? So for the standard form LP, this is very straightforward. But strangely, we have this one. Okay. The theorem says that the complementary slackness is this one. Why? Now, a symmetric form, assume. Okay. Try to, in the standard form, what is this, by the way? This is 0, am I right? In the standard form, this is 0. And what can you say? Anyway, in the standard form, you can show that this is nothing but the lambda transpose X equals 0. So work on the symmetric form. Got it? Then you can show this. First, you can show that this is the complementary slackness you obtain from the primal problem. So it's like this. You derive you write the primal problem for the symmetric form, and you write the dual problem for the symmetric form. Now you start from the primal problem and try to formulate the Lagrangian. Then you have to introduce Lagrangian vector, and you have complementary slackness. That corresponds to this one, if I remember correctly. And you start from the dual problem, and dual of dual is primal. So while deriving the primal back, you will see this. Anyway, so this is showing this one is your 6th additional homework problem. Okay, so let's move to the next topic. Yeah, this one. Now, the lecture note does not say why suddenly we talk about feasibility problem. Here, anyway, the feasibility problem is related to these two symmetric form LP, symmetric form dual. And we've seen the strong duality requires this one. And you see the second line and fourth line is from the primal feasibility, and third and fifth is from the dual feasibility. Got it? So it seems that as far as you can find X and lambda satisfying all these conditions, actually that is your optimal X and lambda. So and also you may say that you can show that by using the complementary slackness. Okay, this is nothing but the condition that X and lambda satisfies complementary slackness and strong duality. And you remember from our general study, if you can find those X and lambda and nu satisfying what? Kkt conditions, then what? In your convex optimization problem, you have the optimality. Am I right? And the linear programming problem, if the solution exists, is a convex optimization problem. So you just need to find x and lambda and nu, possibly, that satisfies some equality and inequalities. That's all. So it seems that just ignore our study about simplex algorithm and search algorithm. Just consider a feasibility problem where you find any pair of x and lambda that satisfies these conditions. And the authors want to say that solving that feasibility problem is as hard as solving the primal linear programming problem or dual linear programming problem. So that's what is written here actually. The reason why, as I told you, suddenly we have that one is that complementary slackness and strong duality turns out to be necessary and sufficient condition for the optimality in the linear programming problem. Let me repeat. This is related to what you need to show in this additional homework. Was it 2? No, this one, right? The relation between convexity and Kkt condition is that if you can find x lambda nu triplet that satisfies Kkt conditions, which include what? The complementary slackness and some. And problem is convex, then what? This condition is necessary and sufficient for the optimality. And linear programming problem, as I have drawn Venn diagrams, you remember that, is what? Is a special convex optimization problem. Got it? So you are finding the optimal solution for the primal and dual is equivalent to solving a feasibility problem. However, the authors say that don't be misled. The feasibility problem is as hard as the original LP problem. Yeah. So you find any x lambda subject to this inequality. And that is the feasibility problem. But it's difficult. Anyway, so I think I'm done with this linear programming. Okay. The next topic is very important and interesting, but it's confusing. Okay. I also, when I kind of organize this course, I many times thought about just removing this chapters 20 and 21 part of your textbook, because it looked like me simple Kkt conditions, listing just Kkt conditions, but it was not. Okay. While I preparing for the lecture, I found I read my own note 20 years ago, written 20 years ago, and found that I should not do that. Okay. So first, let me emphasize a lot what's the difference. Okay. So here, chapters 20 and 21. What is the title, by the way? The title is, let me see, General Constraint Problems with Equality Constraints. So here you have mean f0x subject to h of x equals 0, and here you have min f0 of x subject to f of x less than or equal to 0 and h of x equals 0. By the way, I'm not going to follow the notation in our textbook. It's confusing. I'm going to keep the Stephen Boy's convention. So I will use f0 for the objective function, f underscore for the inequality constraint, h underscore for the equality. And I will stick to lambda as non-negative vector, and nu, that is the Lagrange multiplier vector for the equality constraint function. Got it? So given these two, I'm not saying any duality, okay? Here I'm not saying any duality. That's the difference actually. What I'm saying is this. So the results, let me write down this. So results looks like this. We have 3 results. First one is FONC type result. Second one is that the second order necessary condition type result. Third one is second order sufficient condition type result. So we have kind of 6 theorems. Got it? We have 6 theorems to study. I'm kind of providing you an overview of 2 chapters because I'm going to cover these chapters very, very quickly. So we have 6 results. And they are all in this form. Okay. If X star is optimal and regular. Okay. By the way, about this condition, I'm going to define later. Okay. I'd better say local. Okay, be careful. Is a local extremizer and regular. Okay. Then something. Here, X star is a local minimizer and regular. Then something. If X star is a strict local minimizer and regular, then something. Got it? So these theorems are different from what we've seen in the duality, where our theorems look like this. X star is primal optimal and lambda star, nu star, that pair is dual optimal. And for example, strong duality holds, then something. Got it? So there, we formulated implicitly our dual problem and solved our dual problem. Got it? Here, we don't say anything about dual problem, even though dual variables, Lagrange multipliers, will appear. Got it? So explicitly, we say nothing about dual variable here in the assumptions. Actually, same here, okay, as the left side. The difference is that we have this inequality constraint function. Now, what is this then part? Then part now is related to the Lagrange multiplier. Nu star exists such that, okay, got it? So if X star is local extremizer, minimizer or maximizer, and regular, I haven't yet defined what does this mean, then some vector nu star exists that satisfies some conditions. And these conditions are actually what? The complementary slackness. No, not for this nu. This is for the something like such that gradient of f0 x star is a linear combination of gradient of fhi x star. Okay. And you may say that, oh, wait a minute. It seems that I was talking about Kkt conditions or Lagrange condition. Actually, this is Lagrange condition. It's called Lagrange condition from the historic development. Originally, people studied this problem. Euler and Lagrange studied this one. So the FONC, I said FONC type condition, this one, see that you have first order derivative, right? This condition is called the Lagrange condition. By the way, here you may wonder why nu and this is related. Actually, nu and these vectors are related that way. Gradient of f0 x star plus, let me see, yeah, gradient f h1 x star dot 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 gradient hp x star and nu star equals 0. What does this mean? See that? This is a vector, right? If you evaluate at x star, these are all gradient vectors, right? Now what? This is a vector, so this matrix times vector is a linear combination of these vectors. So, as I told you, this is a linear combination of this. But in this form, not arbitrary. We have this new vector involved here. Got it? And some of you already noticed that this is nothing but, right? Nothing but what? The Kkt condition, the first order type Kkt condition. You formulate the Lagrangian function L of x nu and apply derivative with respect to x and set it to 0. And actually that is same as this one. You remember? U j h j x, right? This was the Lagrangian for this problem, right? Now your Kkt condition is what? Kkt condition is that you differentiate with respect to x and evaluate at x star and nu star and set it to 0. So actually, this is what? This is the special case Kkt condition, excluding that slackness and feasibilities, that differentiability part only. But be careful. As I told you in the beginning of this part, in our duality study, the theorems looked like this. Okay? If x is primal optimal, and lambda star nu star are dual optimals, and strong duality holds, then something. Got it? But now the theorems are different. X is a local extremizer of the kind of primal problem. I haven't said anything about dual problem, right? This problem, then nu exists satisfying this condition. So it's an existence theorem. Got it? And this is very, very useful in solving general unconstrained optimization problem where you don't know whether strong duality holds or not. Okay? Before, in our study, we almost every time assumed strong duality to have something interesting. Am I right? But now, we don't need that. Got it? We don't need to even formulate the dual problem. And similarly here, then, so the assumptions are same as the left side. Then lambda star nu star exists such that here the difference is that lambda star is greater than or equal to 0, as we defined in the duality study, and satisfies this one. Gradient. Got it? So this is another existence theorem. Okay. So what's the use of this one? This is the. What is this one? This is a necessary condition for such X star to be a local extremizer. Okay. So suppose you are given a problem and there are several local extremizers. And this is important, some of the local extremizers are regular, but some may not. Then this theorem is useful in finding local extremizers that are regular. Okay, be careful. Sometimes your local extremizer may not be filtered out by this condition, because there may exist some irregular local extremizers. But interestingly, in many cases, this regularity condition holds. What does that mean? You are given this problem and you can find any candidate solution, any candidate local extremizer by solving this part, by finding nu and x star that satisfy this condition. Same holds here. Got it? So these theorems are more useful. Remember, before we had what? The theorems like this. X star is primal optimal. So we have to show that is optimal. And second, lambda star and nu star are dual optimal. And satisfies something. Under strong duality. Right? And in many cases, it's not easy to show that strong duality holds before we solve the problem. Of course, in convex optimization problems, the Slater's constraint qualification is very, very powerful. That's why convex optimization theory has this thick book and very powerful and useful and used these days. But we are not just given convex optimization problems in many cases. Sometimes we are given some highly just nonlinear constrained optimization problems with equality and inequality differentiable, fortunately, equality and inequality constraint functions. In that case, this may be the only way, got it? Without strong duality. So that's why this is important. Now, for the second part, the story is like this. It exists such that the FONC, these conditions, holds, and additionally, Y transpose, Hessian of L x star nu star. Y is greater than or equal to 0 on Y in some subspace called tangent space at x star. So as you see, this part is for the first order part and this is for the second order part. By the way, how can you obtain this Hessian of Lagrangian function? You find the Hessian matrix and you find the Hessian matrices and sum up. Then it becomes this matrix. Got it? And it seems that it's related to the positive semi-definiteness of this Hessian matrix. But be careful. It's not the positive semi-definiteness of the Hessian matrix, but positive semi-definiteness on this subspace for Y. And I will define what is this tangent space later. Got it? And another one, the second order sufficient condition is that then there exists nu star such that first order necessary condition holds, and Y transpose D star L x star nu star Y is strictly positive for all non-zero 0 and non-zero y and y in the tangent space. Okay. So you have this condition. So it's kind of what? Strict sense equality that is related to the strict local minimization. Okay. So these T are the same. Now, for the chapter 21, the story is like this. Then lambda star, nu star exists such that first order necessary condition and y transpose is the L x nu y is greater than or equal to 0 for all y in the this is a little bit different. Let me use like this. Okay. This is a kind of a tangent space defined not only, by the way, this tangent space is defined by h's. But here, this tangent space is defined by h's and some f's that is related to this dual variable. So this is different. And here you have a strict local minimizer part. Then lambda star, nu star exists such that first the necessary conditions are met and lambda star nu star y is greater than 0 for y non-zero and y is in the tangent space. But here this is little bit different. Got it? By the way, this space is different from this space. Here, these two are the same spaces. So this is a summary. And I'm going to cover this tomorrow night. Probably within just 1 hour and 15 minutes. Okay. So let me repeat. These theorems are all existence theorems and requires regularity. But it's very useful in many cases. Even if you don't have convexity. Okay? That's very important. Even if you don't have convexity, these are very useful. Sometimes you can show that every feasible x is regular. Then what does that mean? Every extremizer is filtered by these conditions, these necessary conditions. Got it? So it's very useful and different from the strong duality lemmas we've studied. Okay? Got it? And fortunately, it's very easy to remember because as you will see that here, we will see complementary slackness type thing involved here. Okay? And as you see that you see again the Lagrangian functions. You don't derive the dual function, but you just need to simply state the here of course L is okay, defined differently. But anyway, you just need to formulate these two functions and differentiate once and twice. Got it? So we are going to see very, very powerful results. And you may use it to find the optimal solution. Okay? Anyway, that's all for the day and see you tomorrow night.